4.5, differentials. Differentials, that's the man Isaac Newton. Part of your misery is on hand, or else we create calculus. Right? Let let y equals f of x be a differentiable function. And you can take a derivative of it. Okay? The differential, dx, is kind of considered an independent variable. Okay? The differential, dy, is dy equals f prime of x times dx. Okay? Now think about it this way. That's a little bit confusing, but let's break it down. We're used to seeing this. If we're given that y is some function of x, that dy dx, that represents the derivative, right? F prime? Yeah? Yeah? So what happens if I perform some algebra to this? What if I said dy over dx equals f prime of x, and I just multiplied both sides by dx? Does this go away? Yeah. It goes away. So dy equals f prime times dx. Now, in these instances, they'll give you the value of dx to use. Okay? So it's not really that good. It's just one more little tiny thing they throw at you. All right? So let's take a look. For the given function, find dy, then evaluate dy for x is negative 2 and dx is 0.1. And they give us the equation y equals 2x over 1 plus x squared. So first off, before I do anything, what's the derivative of that? What do I got to use to find the derivative of that fraction? Low d high minus id low, draw a line and square root. So it is. Here's my low. Here's my high. Low times d high. What's the derivative of 2x? 2 minus high d low. 2x is high. What's the derivative of the bottom there, the denominator? 2x. I draw a line and I square what's below. Excuse me. So I square the denominator. I square this whole thing. Don't FOIL that out. It's fine just like that. Let's just clean up the top. Let's clean up the top. So, okay, I'm going to distribute this. So what do I have to start? 2 plus 2x squared, okay, minus, what is 2x times 2x? 4x squared. All over 1 plus x squared squared. So what can I combine on the top there? This is going to equal what? 2. Yeah, minus 2x squared all over 1 plus x squared squared. Now that is dy over dx, right? Well, they want the differential. They want just dy. So what do? I multiply both sides by dx. So really, dy equals 2 minus 2x squared over 1 plus x squared squared times dx. That's what dy is. You just really still do the derivative. Instead of putting the dx under the dy, you multiply it times the other side. It's the only difference. Yeah, that's it. Now, we found dy. Done. What else they want? They want us to evaluate dy when x is negative 2 at dx being 0.1. So, x equals negative 2 and dx equals 0.1. Just plug in and solve. Plug in and solve. Okay? So, 2 minus a negative 2, 2 minus 2 times a negative 2 squared. All over 1 plus a negative 2 squared. Squared. times 0.1. Here's some calculators clicking. What do we got? So I was throwing my -2 here and here. What'd you get? -0.024? What do we get? Now wait. Now wait. Maybe not. I did this first period. I did a couple problems, and I'm trying to remember what one of them was. What's on top? This is 4, right? 4 times a -2 is -8, right? So 2 minus 8 over. All right, what's -2 squared? 4 plus 1. 5 is when I square it. Well, that's technically 1/10. I mean, I can do it this way. That's technically -6 over 25 times 1/10, which is -6 over 250. Now put that in the calculator. -6 divided by 250, -0.024. -0.024. Now, let's see if we put this in. What was it? 2, where are we? -2, parenthesis, -2 squared. To the top? Yeah. The bottom is parenthesis, before the 1. Parenthesis, 1 plus, parenthesis, -2, parenthesis, squared, parenthesis, and I got to square it, right? Now this is all times 0.1. There we go. It's tricky with all the parentheses and exponents. It's tricky. Gotta make sure we do it right. So that's it. So, what do we have here? Well, we've got to find the derivative. We did the quotient rule, low d high minus ID low, draw a line and square below. Once we got that, we just put the dx on the side with my numbers and variables, the dy alone. And I just plugged in my x and my 0.01. Estimating change with differentials. The function f changes value when x changes from a to a plus dx, okay? Because dx is a small change, okay? And if a goes through a small change, well, the function goes through a small change altogether, okay? So they want us to find the true change, the estimated change, and then the approximation error. Remember, what is it? Back in 8th grade for you guys, a long time ago, was human minus actual all over the actual to the actual value. Remember that back in the day? What was that called? I know, it means I can't remember the name, but it's killing me. I remember it later. But it's something to figure out some sort of error, a margin of error. I don't think it's called a margin of error, but that's what it is. It's called to find a margin of error. Okay, we take the difference between the actual and what it was and what someone actually did it at, the human who measured it. And then you divide that over the actual, and that gives you a percentage. Well, it's kind of, yeah. That would give you the change the decimal into a percentage. But yeah, so it's kind of the same thing, but in order to find the true change, look what they do. Okay? They want you to take the function, and then the homework that's given to you like this, these right here, and the notes I know it's not. But you take the function, and you put in the value a plus dx into the function to figure that out, and just subtract what f of a would have been. That's like taking the actual and subtracting the human, right? They're the same thing. Except the estimated change is just the derivative with a in it. Okay? That's the estimated change. And then to approximate the error, or the approximation of the error, you take the absolute value of the true change, which is a, and subtract the estimated change. You just take that. It's the difference between the two, but it's always a positive number. That's why the absolute value is a. Okay? So let's start with a. And I want to go not too fast, because I don't want to confuse you with these a plus x is a's, f prime of a. I don't want to go nuts. But you guys should know how to input something into a function. If I put f of 5 goes in for every x in that function, okay? So, right now, I gotta figure out f of a plus dx, okay, minus f of just a. And you're probably gonna want to use a calculator because there's decimals involved. Maybe not. Maybe you can go through this quickly. So, here's my function right here. Well, I want to find the function of a, which is 0, plus dx, which is 0.1. So ultimately, I want to find f of 0.1. And then I want to subtract f of a. Well, what's a? 0. And that's going to give me my true change. That's how much it actually changes. So, what's my function? X squared plus 2x. So, for here, it is x squared, so 0.1 squared minus 2 times 0.1, minus, well, this is nice, f of 0. That's 0 squared minus 2 times 0. You see where I did that? I just put that right into here. I put my 0.1 in there, and then I put the 0. Okay, well, this is going to be 0. It's nice. 0.1 times 0.1, is that 0.01? Yes. I'm assuming it is. It's been a long day. Minus 0.2. Who's got that for me? Negative what? Negative 0.19. So, we have negative 0.19. Question? Tommy. That's a plus. Oh. So this should be a plus. So this should be a plus. Just stays a minus. Don't worry, so it's what? 0.21 instead of negative 0.19. 0.21 minus 0. 0.21. That is the true change. 0.21. Good catch, Charlie. Okay? 0.21. Any questions on that? They give you the numbers to put in there, and you just put in the function. That's K. That is the true change. Now let's find the estimated change. I need to take the derivative of this and then put a 0 into it. Okay? So I need f prime of a times dx. So, well, f prime is what? If I take the derivative of my function, 2x plus 2. That's f prime of x. So what's f prime of a? What's my a value? So f prime of a is f of 0, isn't it? Because isn't that my a? So that's 2 times 0 plus 2. What is that? It's 2. It's 2. But don't forget, I still need to multiply that by. So that is 2. So I still multiply it by dx, multiply it by dx, multiply it by dx. What is dx? 0.1. So what is 2 times 0.1? 0.2, thank you. 0.2, you guys are exhausted. So am I, don't worry. So this is the estimated change. So look how close the estimated change to the true change is. It's 1/100. It's 0.01 away. And that's really how we figure out C. the approximation. Okay. So C, the approximation, I take my true change, I subtract the estimate, and I make sure I take the absolute value of it. So it's 0.21 minus 0.20, which is the absolute value of 0.01, which is 0.01. So let's take what we just did and apply it to some situations here. The radius of a circle increases from 10 meters to 10.1 meters, okay? Use dA to estimate the increase in the circle's area. Then compare dA, the derivative of the area. dA, okay? Then compare this estimate to the true change and find the approximation error, okay? So we are going to use it to estimate the increase. So when I estimate things, it says f prime times dx, right? It's f prime times dx. That's what we're using here. What is the area of a circle? No, pi r squared. It is pi times r squared. We said nothing of the sort. No one mentioned length whatsoever. Okay, or width. Pi r squared. Okay? Stay with me, stay with me, stay with me, stay with me. Stay with me. Area is pi r squared. So what is the derivative of area? 2 pi r. Okay? But now, if it would have been like this, we're using differentials, right? We're going to say, if we're going to take the estimation, don't we need to multiply it times dx? Yeah, our estimation. Remember, what happens when I take a derivative? Exponent comes down. That. It's the last period of the day, folks. I want to go to. Now, let's figure this out. Okay? 2. Okay? 2 times pi, which is in our calculator. We don't even have to type it out infinitely. What's the radius? 10 times dx. What's dx? Or in this case, why do we not say dx? Ooh. Why is it dr? Well, because it says dr here. But we always do that. It's divided by whatever variable we're taking, d to the r. So that's why it's times dr. This problem here is dx because an x is inputted, so that's why I use dx. Okay, just want to point that out. Whatever variable is in the equation, it's d times that variable. Okay? So, what is dr? Can I trust you guys to put that in your calculator and round that 2 decimal places? Okay, first of all, what is 10 times 0.1? 1. It's 1. And what's pi? 3.14 if I double it? 6.28. It is. So that is 6.28. Okay? Okay. What we just figured out here is the estimated increase to the area from 10 to 10.1. We're saying that based on the derivative, the area of that circle will change by 6.28, which is 2 pi. Same thing as 2 pi, right? Now let's find the actual change. How do we do that? Without taking derivatives. How do I find the actual change? Any guesses? Yeah, use the area formula. Yeah, take the area of the circle at 10, then take the area of the circle at 10.1, and that will give you the actual change, right? So if I do pi r squared, well, I do pi times 10.1 squared, that gives me the area of the bigger circle. Then I subtract the area of the circle before it changed, 10 times pi squared. Like a factor out of pi. And then I got 10.1 squared minus 10 squared times 5. But why don't I just put that all in the calculator and hit enter and give me 2 decimal places? I mean, I could factor and figure it out that way. It's 100 and then, decimal slide it over. But let's get crazy here. Okay, I want more than one answer to make sure that it's correct. 6 point what? 3.1, is that what everybody else got?
Yeah.
6.3. So that is approximately 6.31. Wow, now that's close. Now that's close. So if this is the actual change, and this is the estimated change, how do we find the approximation error? The difference between the two, I'm going to take the absolute value. Okay, so yeah, it's the actual, I should have called that true. It's the actual or the true minus the estimated, and I just take the absolute value. So 6.31 minus 6.28 is 0.03. That is close. That is good. When there are things that matter that are in the line, you want to have a very, very, very slim margin of error like that. Okay. So, estimating change of differentials. In the 1830s, French, there's no C there, physiologists, right? I was going to say, hey, that's why I paused before I read it, because my mind wants to put the C in there. Okay? So, in 1830s, French physiologists, John, and that's John, okay? Poisson. I guess that's how you pronounce that. And I shouldn't be laughing because this guy made a major contribution to people here. I discovered the formula that we use today to predict how much the radius of a partially clogged artery has to be expanded to restore a normal flow. And in case you don't know, normal flow of an artery to any place, especially the heart, is very critical. And this guy did in 1830. So his formula, V equals K times R to the fourth, says that the volume of a fluid through a small pipe or tube, in this case an artery, in a unit of time at a fixed pressure is a constant times the fourth power of the tube's radius. So K is some sort of constant, and R is the tube's radius. Okay? How will a 10% increase in R affect V? So, if V equals K R to the fourth, all right? What's that estimated change going to be? What's the estimated change going to be? I got to find dV with respect to R, right? Because R is my variable. So what's the derivative of that, KR to the fourth? 4K R to the third. Now, what do I have to do? Listen, one more thing I have to do, one more different step. Correct. So, my change is going to be 4K R cubed times dr. How will a 10% increase in R affect V? So we're going to figure out how is this going to have an effect on this, okay, in percentage-wise. All right, well, a percent is really a fraction. It's a ratio, isn't it? With respect to V. Okay? So, what is dV? Oh, we have it right here, don't we? 4K R cubed dr. All over, what is V? It's the original, right? They want to know how it's affecting this. So that's K R to the fourth. All right? So, they want to know it. An increase to R. Okay? This is the big thing. It's a 10% increase to R. So let's kind of simplify this as we have. The k's cancel, right? So it doesn't matter what happens to the r, the k's a constant. That's not going to make any effect to it, will it? You see what I'm saying? All right, we have this number 4 out here. What can I do with these r's? Yeah, 3 cancels out with 1 here. So I have 4 times dr over r. This here is what they're saying the 10% change in the 10% increase in the radius. How will it affect v? Well, if that changes by 10%, what's 4 times 10%? 40%, or 0.4. If you want to make that, Tom, you were saying it should be 0.1. If you wanted to make this 0.1, that would be 0.4. And of course, the percentage is 40%. You see what I'm saying? So I was trying to kind of figure out an easier way to tell you that. But the change with respect to the original, how will it affect the original? We'll compare. You want that percent, right? Create that fraction. And here you go.